So Rasmus, you survived the ENC, huh? I just saw that you were at in Florida.
Yeah, it was a pretty quick stint to Florida and back, but it was nice. So I think the size of the conference, the people that were attending, it was not at the usual number of attendees. I'm not sure. I didn't count. Obviously, I didn't get any real numbers. My gut feeling says it's like, I don't know, only 2/3 or half of the people attending. So not too many.
I think it's about 500 people. That's what I heard.
There were 500, yeah.
And so usually what do we have, like 800?
Yeah.
Yeah.
Okay. I mean, at one point in the past, long time ago at ENC in Boston, it was at 1,600.
Wow.
It hasn't been that large in a while.
Yeah, I think before Euromar started being very regular, this number was in the thousands. And Euromar took a lot of audience. That makes sense. So, but I think, this year, if 500 people show up and most people didn't get sick, I would count that as a success. So I don't know.
Len Müller has put precise numbers into the chat.
Yeah, 500 in person, 85 online. So,
Hi, Len.
Everybody. Hi, Bob.
Hi, Lauren.
good morning, afternoon, Lauren.
Good morning. Yeah.
Yeah, no, it was still great to be back in touch at the ENC and really see everyone again in presence. Had lots of discussions at posters and after the talks, and it was really good to have this again. Even though, of course, the seminars or ZOOMinars have been great and are still great as an easy to use additional tool, but it was also nice to just see each other and just chat.
A lot of things that get transmitted in a person-to-person conversation just don't go over Zoom with one region or another. Yeah. So it's yeah.
Particularly if it's being recorded.
Yeah. For posterity, right?
Cool.
Yeah. So Euromar is maybe the next big event. In Utrecht. So, and then May is putting on a party in August.
Oh, it's going to be great. I hope all of you will come.
She's offering free airfares, free hotels. Huh? Right?
There's going to be a very nice banquet. If the science is not enough to entice everybody, we're going to put everybody to a courthouse. Right, Bob?
So you decided to go to the courthouse. Okay.
We're going to invite everyone to a courthouse.
No,
it actually is a very beautiful architectural place near the harbor, and it sounds scary, but it is a very...
I mean, I picked that out with Gerhardt. It actually is a nice place.
It is a nice place.
It's right in the harbor, and if there's not a tornado or a something coming in from the a hurricane coming in, it'll be great.
A blizzard.
There probably won't be a hurricane in August. It's too early. Yeah. But no, that is a nice venue. It's a beautiful venue. Yeah. It's where what's his name was convicted.
I don't know.
The guy who just Whitey Bulger.
Huh?
Whitey Bulger. He's a very famous mafioso, right?
I think that's the brother of the UMass president, isn't it?
He is, as a matter of fact.
Yeah.
He was. He's no longer alive, but yes. But he was convicted in that space. So
I see. Okay.
Yeah. So it's a famous location.
When are we starting? 5 past or 10 past?
Well, five after. So MIT classes start at 5 after the hour.
Okay.
So we follow that tradition for whatever it's worth. Yeah.
In Germany, we have this 15 minutes delay between the full hour and everything starting. Always.
Yeah. Okay, so it is 11:05. So why don't we get going? All right. Welcome everyone today to the ZOOMinar, the Tuesday, 10th of May ZOOMinar. We've got two really outstanding speakers today. Paul Schanda from the the Institute of Science Technology in Vienna, in Austria, and Rasmus Linser, who is now a professor in Dortmund. And the first speaker will be Paul, and he's going to tell us about dynamics in large protein assemblies. If you want to look at his his curriculum vitae, his resume, it's on the announcement. He was a PhD student in Grenoble and also worked as a postdoc in chemistry and applied sciences at the ETH. He was then a research team leader at the Institute of Biological Science, I guess, in Grenoble. And now, as I said, he is a professor at the Institute of Science and Technology in Austria, Vienna. Okay, so Paul, the virtual floor is yours.
The kind of systems that we are looking at.
Okay, good. So I guess you can all see my slides.
Yeah, that's good.
Okay, perfect. Good. So apologies to the ones that have already seen the ENC talk. There's quite a bit of an overlap. But anyway, so I'm very grateful for being invited to this ZOOMinar, and it's very nice to be a part of this. And yes, so yeah, I guess what I'm going to be talking about is high dimensionality solid state fast magic angle spinning solid state NMR. And let me just, okay, now it's working. Good. So increasing the dimensionality is something that is nothing new and has been done in order to disperse shifts more effectively for decades. And effectively, we've come to 40s, even already in the 90s, in work, for example, by Lewis K. And then with the onset of non-uniform sampling, even 50s, 60s, 70s have been prominent, particularly for IDPs. And that's owing to lots of bottlenecks that have been overcome successively, labeling schemes, and then, as I said, the sampling issue. Sensitivity is something that is still an issue because with every dimension that we add, we are obviously losing some sensitivity of a factor of square root of 2. And so the problem is that usually we want these experiments for molecules that are problematic in the sense of having a high level of complexity, which means a lot of residues normally. And particularly these high molecular weight targets, they are associated with pretty short coherence lifetimes due to their tumbling correlation times. And as such, we have big losses in any evolution periods, added evolution periods, and added inhib transfers. So we would be kind of stuck with pretty short experiments or lower dimensionality experiments in that respect. And so as a consequence, usually NMR, as all of you know, is usually stuck to rather small proteins if we are going for backbone assignments. And that's obviously something that's a problem. And solid state NMR in that respect is something that's advantageous because on one hand, in particular, if we go for fast magic angle spinning and also deuteration and a combination of these two, depending on the speed or the rotor frequency, finally we end up in a condition where we do not need any high power decoupling anymore. And also we can then add paramagnetic doping, and as such we can go for very fast recycling, up to 3 scans per second or even more. And also due to the fact that we have these deuterated conditions and fast magic angle spinning, we have very high transfer efficiencies and very long T2s. So that's really the basis for building high complexity pulse sequences. And the nice thing is that this as Paul already also mentioned. And what is nice about this is that this doesn't work only for small proteins, but that basically there's no such thing as a tumbling correlation time, and the coherence lifetimes are only dependent on the sample conditions, maybe dynamics, as well as the rotor frequency. And so that means that basically we have the same efficiencies, the same long coherence lifetimes also for high molecular weight targets. And those are obviously the proteins that really need these more sophisticated magnetization transfer schemes, including high dimensionality. So there are a few such messages having been conveyed over the years, some by us, some by others. This is, for example, also a work by in which Lauren has been involved, by Guido Pintakura. All boils down to the same message. In the solids, we have the same relaxation times, and that also then correlates with transfer efficiency. And so finally, the bigger the system is, and the higher the complexity, or the more transfer steps and evolution periods we have in indirect dimensions, the more solid-state NMRs in fact become advantageous compared to solution NMR, regular solution NMR, if we're focusing on backbones instead of methods, for example. Good. So as a consequence, 4D NMR is something, solid-state NMR has been proposed for a long time. There's just a collection of examples here. This is by Jet Weenstra's group. There are a lot of things that we have done. This are just different 4D RFDR experiments, like 4D HSQC, nosy HSQCs in solution, in time-shared fashions, in diagonal compensating fashions. Here in a dream version, this is by Beat Meyer, but principally the same thing. Then actually something that Paul just talked about in his slides also, these are HNC-ACO or HNC-OCA based experiments, which we came up in a 4D fashion here in these papers. There's 4D amide to amide assignment experiments. So this is something that I'm going to talk about in more detail in the next slides, where we connect one amide pair with the next amide pair directly. And there's also such things that HCCH 4Ds by Teresa Calomagno's group, and also 4D sidechain to backbone experiments, where we correlate all of the sidechain experiment atoms, in this case, as in a 4D version, only the carbon shifts with the C alpha, the N, and the H. So there's lots of 4D experiments. And in fact, I want to just jump into more details for this amide to amide experiment, because we need that as a basis for understanding what comes afterwards. And so originally, when like solid-state NMR, proton-detected solid-state NMR was in its infancy, we and others basically just copy-pasted the solution NMR approaches, having, for example, HNCA plus HNC-OCA, HNCO plus HNC-ACO, or HNC-ACB plus HNC-OC-ACB, to get sequential connectivities. And as such, this was all based on carbon-carbon matchmaking. And the problem is that works for small molecules, but for big systems like this one, tryptophan synthase that we've been working with in collaboration with Len Muller's lab, then we see that really both the CACO plane is heavily overlapped, the CACB plane is heavily overlapped, and even the triple matchmaking with CACB and CO only gives rise to less than 40% unambiguous connectivities. And this all comes on top of the NH matchmaking that is kind of restricted by the overlap in the HN plane. So these experiments that correlate amides with amides, they're very beautiful, because they really completely cancel out this carbon-based matchmaking, and they are very intense in terms of their signal intensity. So we get to around 8%, 8 to 10%, I should say, with respect to the amide HNH, which is kind of the solid-state HSQC, which we always use as a reference. The problem is that still sequential linking hinges on the HN resolution, and also that in these kinds of experiments, we somehow need to correlate these sequential connectivities with the residue type information, which comes from, for example, from an HNC-ACB or the sidechain to backbone experiment that I just alluded to. And so again, this is only a 2D like HN match between the sequential connectivity and the residue type. And so if the HN plane is totally clean and there's no overlap, then such an HN connectivity can in fact be obtained by just correlating, for example, H and NH and N and NH, making it a pseudo 4D. If we do have some overlap, a 4D is better, and it really comes at the same costs, because if we have two 3Ds or this one 4D, that basically, if it's the same coherence transfer pathway, then this is pretty consistent. And the best thing would really be to have a 5D that in addition includes the C alpha chemical shift or one kind of carbon chemical shift in order to correlate that with sidechain information. And luckily, such 5D processing scripts and strategies have been worked out previously, for example, by Viktor Krzminski's group in Warsaw, and we've been very constructively interfering with them. And so the basis of these methodologies is that, I mean, the problem really is in processing these data that usually these would be terabytes of data, but the trick here is this SMFT, the sparse multidimensional Fourier transformation, where we basically use a basis experiment, for example, defining the peaks of an HNCA, and only at those positions we dig out the 2D planes of the remaining two dimensions. So we get these 2D, basically a stack of 2D planes, and that is then only on the order of less than megabytes, I guess. So that's pretty nice. So all the empty space is not processed. And then we have the C alpha information, and we can, for example, make this matchmaking with the HNC-ACB type of experiments. So I just always call them by their solution NMR name. So that would be an HNC-ACB. That would be this kind of, yeah, if you want, CCCONH TOXI experiment, for example, in 4D. So, and making this matchmaking with the C alpha included really reduces the ambiguity with respect to like linking sidechain information to the sequential information. These experiments come in two flavors. For example, written HNC-OCANH and HNC-ACONH, where we go either backwards or forward. And we could use as a basis for this experiment, for example, the HNCA, but we could also use the HNC-ACB, and we just use the C alpha chemical shifts out of this experiment. And then we find for these three coordinates, H, N, and C alpha, we find the next residues, H and N chemical shift. So shown here for the glycine, the same thing here. For Q50, we find the next residue, G51, H and N chemical shift. So the HNC-ACONH just goes backwards. And then we find, for example, for G51 peak positions, which we use as a basis from the HNCO experiment, we just find the previous, the Q50 HN peak positions. So the pulse schemes are pretty simple. We just go from H to N, from N to C, and then we have a CC transfer, which usually we go for using Besch CP, and then we have from C to N, from N back to H, before we only have this Mississippi kind of water suppression. And obviously there's an evolution period before each transfer. And then if we have the other pulse sequence, that really is kind of the same. We just have this inverted Besch CP, which I don't have the time to go into details for. Good. So the question is, what is better? And Paul also alluded to this one. In fact, that 1.3 millimeter probes are more sensitive. And that's just if we have the deuterated samples compared to 0.7 and fully protonated samples, just due to the higher transfer efficiency. And so it boils down to 8% of this bulk sensitivity compared to an HNH for the 1.3, and only around 4% for the 0.7 situation. And this is just for a small protein in the SH3 domain of chicken alpha spectrine. After 6 days, so that's not kind of what we really need. We get all of these residues, and we only get 41 out of 48 here that can potentially be assigned. There are some flexible loops and stuff, There's less for this situation in the 0.7 millimeter rotor after 8 days. The other question is what's better, BASH CP or INIP, and this is really very similar. So in 1.3, it seems like the BASH CP performs slightly better. For 0.7, it's really totally identical here. So we would stick with 1.3, and we only have the back exchange issue that's something that we're working on also pretty actively regarding labeling schemes. But other than that, it's the more sensitive approach, it seems. So is it a realistic approach? And so we have these two experiments, as I said. In fact, they are similar. The backwards way is a little bit less sensitive, going down to only 6% instead of 8%, for example. And this is kind of a benchmark here. So we can record on the SH3 domain. As I said, it's like 64 residues. We can get a nice 5D data set within 1.5 days. So we're definitely not in the resolution limited regime. And we still get a really nice signal intensity. So for NUS data, it's always a little bit difficult to really judge about signal to noise ratio. So it all depends on artifacts, but let's say this is a good number, I think. So it's really reliable. Everything pops up. And if we convert this or translate this to bigger systems, so this is tryptophan synthase again. As I said, Len Müller's lab made this, in particular Varun, when he was a PhD with him. And so for this, we decided to record this over 30 days, and we still get a very nice signal intensity for these correlations. Not for everything, because there's back exchange issues, there's dynamics for a certain portion of the residues, but in general, this works really nicely. The nice thing about these pulse sequences is also that they can be recorded simultaneously with multiple other correlations, and that's now something that Guido Pintacuda's lab did, and Lauren was also involved here. But this is basically work by Jan Stanek, if I know correctly. So these sequences can be recorded in such a fashion that very different kinds of correlations can be recorded at the same time, which overall shortens the measurement time involved drastically. So for our 2 × 72 kilodalton tryptophan synthase, obviously we did not only record one such experiment, but we recorded all the other experiments that we could in addition, and then we also collaborated with Peter Güntert to get computation assisted assignments going using Flyer. And this all boiled down to on the order of 60% of the residues where we got reliable H, N, CA, CB, and CO shifts, and some others where we got just part of this collection. So that's definitely not yet a complete assignment, but it enabled us to really tackle biological questions. And so this is something that Len Müller's group is very good at. And they calculated shifts for this lysine sidechain and the beta subunit active site. And then for different protonation states, they would calculate different chemical shifts based on first principles calculations. And then the experimental shifts do in fact match only with the calculated shifts if we assume a fast exchange 60/40 ratio. And that's something that's also supported by Bayesian probabilities. And we can use that in order to get temperature dependent data. Something that was constructively suggested by a peer reviewer. So thanks for that. That was really making the paper stronger. And we have line shape analysis. And in addition, we have the knowledge that in the crystal structure, there's already this terminal helix is not totally rigid. And we have at least preliminary relaxation data. So this is really only R1 row data. Not relaxation dispersion because of the measurement time that yet we did not really want to invest. And all of this boils down to have an automeric exchange that is between these two forms, but that is not an isolated event, which would be on a much faster timescale than what we observe here on the basis of these line shapes and also the activation energy from the temperature dependence, but it is a modulated event that must have to do something with overarching electrostatic properties of the pocket that are somehow changing over time. So then if we come back to this technical aspect that the talk was supposed to be on, so the 5D would be better if we have even more overlap. It would be nice to have, in fact, a 60. So that would really go for really resolving one residue with 3 chemical shifts, and then we would have a second residue again connected via 3 chemical shifts. So 60 is something that's difficult to do. It could be potentially constructed as a pseudo 60, so that would be an HNC-H, HNC to H, HNC to N, and a third 3D, which is HNC and C, which would give us all the connections that we want in case this HNCA is free of overlap, which is kind of okay even for TS. Even better would be, in fact, having a 5D HNCA plus H and N, and then this third 40, which is HNCA and this other CA. So with this, we would really get a totally unambiguous connectivity. And that's something that we tried at least. So that's really work in progress on the small SH3 domain. And we get, in addition here, this, for example, if we take the V23 as a basis, we get the next residue T24 chemical shift of the carbon. And this can be recorded in within 18 hours here. And if we combine this with the 5D that I just talked about more lengthily, then we have all of these shifts and we can really get unambiguous assignment without even knowing anything about residue type. So this is without any HNC ACB. Again, this is only for a small protein, but I think it's really, really useful for larger systems. Good. So last thing that I just jump on quickly is that these 5D experiments can also, the techniques can be applied for sidechain to backbone experiments. And that's something where the motivation comes from the fact that, in fact, backbone folds we can obtain pretty neatly even from deuterated and back exchange systems, but really high resolution structures, including the aliphatic residues in the center, we really need the aliphatic protons for, and a lot of distances to get this converged nicely. And so this is something that I don't have the time for to go into detail for, but that's another kind of work that we've been heavily working on, basically getting, in the sense of RFDR, distance restraints to have time-dependent data buildups to really get highly precise distance restraints here. And the basis for all of this is really assigning these aliphatic protons. And even for this small 64 residues protein, this we can do if we have 0.7 millimeter rotors and full protonation. So there's no deuteration involved now. And we can get access to all of these aliphatic protons in addition to the amides, but still these 2D planes are hopelessly overlapped. And then one approach would be a 40H CCH experiment to really get the, let's say, in a toxic kind of fashion to get these spin systems going. But then the bottleneck would be the H alpha, C alpha dispersion to connect this with the backbone. And even for this SH3 domain, we really have a lot of overlap in the H alpha, C alpha. And this obviously would become much more devastating if we have inhomogeneous contributions or larger systems. So the remedy, or the question is, can we obtain unambiguous sidechain experiments, sidechain HC assignments? And of course, a remedy would be the 5D sidechain to backbone correlations, which would correlate all of the HC, let's say, toxic correlations here of the sidechains with the backbone H and C. And so most advantageously, this would have these HN and C 3D coordinates for these 2D toxi HC planes, let's call them. I'll just say something about a 4D version in a minute. Good. So if we look at the individual planes of these HC sidechain, intra-sidechain correlations, there are really many that look very similar. And for example, if we overlay all of these, which have the same H delta, C delta peak here, this is what it looks like. And that's in fact what we would get if we only had a 4D now here at the, let's say, these two indirect dimension coordinates. And in fact, we can decipher all of these correlations if we have this backbone resolution or the backbone dispersion. So that's really highly valuable whenever these sidechain correlations are in the focus. And that can also be used very easily, obviously, also as a 4D. So we don't necessarily need the C alpha if already the HN plane is resolved. And then it would be a straightforward, basically reduction of one more indirect dimension. And then we can also process this without the Koszminski SMFT approach. It's a little bit easier then. What's a little bit more complicated by contrast is that we can also concatenate, for example, this 5D experiment with an intra sidechain 4D HCCH, because there's lots of magnetization left on the carbons on C alpha, for example, because not all of the C alpha magnetization would be transferred to 15N in the CP step, but even more on the C betas, C gammas, C deltas, and so on, which just don't have a 15N next to them. So we can just use this orphaned magnetization and then also store this for some time on Z and then transfer it again to H, to protons, in this case, the aliphatic protons, just using a second buffer, which is something that's easy to do with the new neoconsoles of the Bruker systems. So then this is a little bit more complicated. So the 5D, we basically have to split the data. The 5D is just processed the way I just talked about, using the amide to amide correlations. And the 4D, that's something where we basically have to merge down or project down the 5D information into 4D. So one out of the indirect dimensions, they're the real and the imaginary data, inclusive all the incrementation steps. They are all redundant. So we basically have to just merge all of these identical FIDs to finally get a 4D data set. And then we can basically use the 4D and the 5D at the same time. And together, this really gives a totally comprehensive assignment. Again, this is for this SH3 domain of the sidechain, HC correlations with really a lot of shifts coming out of there. So then this is the basis for structure calculation, which I don't want to go into detail for now. And the very last slide would be that next thing could be really designing experiments that are, let's say, a minimal number of experiments from which we get complete assignments. So in this experiment, or in this example, we're just combining an HN, CA, CO, and H experiment, this 5D backbone or 5D amide to amide experiment with this 5D sidechain to backbone experiment. So we don't need any HNC ACB or something. And then we really get all of the shifts of this protein within 8 days of measurement time at 700 megahertz. I mean, the COs are missing here. And obviously, this is only a first try in this direction, but really the dispersion allows things to be done that are highly effective. So in conclusion, we have the possibility of really generating very long coherence lifetimes and also very short recycle delays in the solid state. And so we can get to very complex pulse sequences. And the really important message is that these efficiencies and the T2 times, that's the same for small as well as for big molecules. And so really for the targets that need it, these are the ones that would benefit from these approaches. And so fast magic and spinning brings really important new prospects for high molecular weight targets. So with this, I would like to close. I would like to thank the people that were involved, my current group members, and in particular, Alex, who really did most of the work that I showed today. Also past members, collaboration partners, Len's lab, who did a great job for the tryptophan synthase work, chemistry studies, Peter Güntert, and funding. And of course, I'm very grateful for your attention, and I'm happy to answer any questions.
Thank you, Rasmus. This is a very impressive talk of high dimensionality in solid state NMR. So Hartmut and Paul have questions. Go ahead. Hartmut, do you want to start?
Yeah, sorry, I had to switch on. It's a very short question. Your experiments where you have several acquisition periods and so on, does that really save time? Because you have to make the duty cycle longer to avoid overheating of the sample. That's my guess. You may say no. I guess it's very important to have lowest low power decoupling and all these, not too long acquisition times and so on. I'm
just trying to get back to the slide that you've had. It's basically something that refers to everything. So I guess really the duty cycle, that's not a problem. So these very sophisticated pulse sequences then can be recorded with the same duty cycles. as what we used to. So we can just go for 300 milliseconds D1, and then it's not inducing much heating. So there's no measurable effect on sample.
How long are the acquisition times then?
I mean, the acquisition times in indirect dimensions, that's something where we don't really have any high power decoupling. I mean, it's really only a scalar decoupling, so it doesn't matter. It's, I don't know, depending.
During detection, you need to have a minimum acquisition time during detection, isn't it?
Yeah, I guess that's something like 50 milliseconds, 80 milliseconds, something like this. So it's pretty good. And the question whether it saves measurement time, I mean, any new dimension will cost you measurement time. That's true. But for a certain complexity of spin systems, I guess really there's no way other than somehow dispersing these resonances, and you will not be able to do that anymore in 3D experiments. You're muted, Hartmut.
Yeah, sorry. I'm not sure that we talk about the same thing. I was talking about the pulse sequences which have two acquisitions, one on the carbon dimension, one on the nitrogen dimension, and so on. Or proton.
Yeah, sure. Yeah, sure. No, that's you basically really get this for free. That's the same framework as what, for example, Manuel Etzkorn has been doing with Utopia NMR. Eric Skrupscher has been doing with all sorts of experiments, and also Jan Stanek and Guido Pintacoda. So I think that's kind of established.
Good. Paul, you wanna next?
Yeah, I just had a quick question. You showed rather in the beginning of your talk a comparison between 1.3 and 0.7, and you show that I think it's 8% for the 1.3 and 4% for the 0.7, and I find this counterintuitive because I understand that the HNH is already lower because you have less sample, but if you spin faster, the coherence lifetimes will be longer. So I would expect a higher percentage of the complex experiments compared to the HNH, which still could be in absolute numbers lower.
No. We're comparing 1.3 and the deuterated case with the 0.7 and the fully protonated sample here.
Ah, okay.
So that's why the coherence lifetimes are longer for the deuterated, even if you spin slower, most slowly.
Okay. And did you ever do that for a deuterated 0.7? 100 kilohertz deuterated?
I think we did not do that, but I think then you would have you would definitely have longer coherence lifetimes, but then you would be losing due to just the lower sample volume. And so then there's no necessity for spinning fast anymore. You have the same sample related issues and bottlenecks, and so just go for 1.3.
Okay.
Okay, so I have some questions about both parts of your talk, Rasmus. So in the first part, I think your SH3 experiment 5D took about 18 hours, right? And when you went to the 72 kilodalton times 2 tryptophan synthase, it became 30 days. Did the time scaling agree with the molecular weight increase and taking into account the line width difference between this small model protein and this large, still relatively well-ordered protein?
Exactly. So the second part is more easily answered. The line width is really maintained. So that is a very nice system to work with. Then yes, if you do the math, it does not boil down to this factor of 100 that you would expect from 64 to 665. But for measurement time, it's really something that there is no sharp definition of how much you need, right? So the more you have, the better. And unfortunately, it scales with a square root of 2. So there's no very hard line how much you should go for. So we just stopped after 30 days. Obviously, it would be better to have more measurement time for that.
And this tryptophan synthase 2 times 72 kilodalton, do you have one set of chemical sheets for 72 kilodalton, right? Yeah. Okay, so it's just a dimer. So then in terms of the information content of the 5D experiment with HN plus the C alpha in the middle, would it be possible to obtain the same assignment information using perhaps 2 4D experiments? I realize it's more work and it's less dispersion, but would it in principle be possible to get it? And if it's possible, would you save time for doing that, in doing that?
Yeah, whether we would save time or not, that depends on how this new experiment is then set up. Probably a little bit, because it doesn't have the same coherence transfer pathway. And then it's, well, I'm not sure. But definitely the dispersion is something that is a problem, because really we want the problem really in this system and in other large systems is that we have the HN plane not being clean. And so we know there's, let's say, 5 residues or 3 on top of each other, and they are associated with the next position, which again has 3 different HN shifts or combinations on top of each other. And then this is totally ambiguous, and only if we have, for this whole pathway, having the 4 H and N shifts, if we can map that again to some kind of agency ECB information.
Okay, so my second question is a scientific question or about the system application. So your phenylalanine information, does that come from a uniformly labeled sample, or is it more site-specifically labeled, where you can tease out both the population and the activation energy? It seems to me that's pretty amazing, because this is such a large system, and you presumably are still doing this in a 1.3 millimeter rotor, or?
You're talking about the lysine, I guess. Lysine.
I thought you were talking about the phenylalanine. Is that wrong? Is it lysine, or?
It's a lysine. So it has all these C alpha, beta, delta,
so
gamma,
lysine.
delta.
Right. So then it's, you had a population, you teased out a population as well as the activation energy barrier. How did you, what kind of labeling did you use to get that information?
No, it's really this uniform labeled system. We only had 1 sample. So that is, so this, we got all the sidechain chemical shifts from there. In fact, for the temperature dependent data that we recorded, we only looked at the HN chemical shifts of the lysine. So that's basically done only using the 15N chemical shift of this N zeta, I think.
So 2D based detection.
This is then 2D based.
I see. And you just have that reasonably resolved in a 2D.
Exactly.
Once you have assigned. Okay.
Exactly.
Okay.
Yeah.
Okay.
And then the rest is line shape analysis, and that is something that we can get the effective rates out, and that is something that can be fitted, and then we can get the basically the time scale again in a temperature dependent fashion.
Okay. Yeah, Lauren.
Yeah, technical question. Thanks for the talk. Maybe I missed it, but I was curious what you were using for the reconstruction of the non-uniform sample data, and whether these adaptations of these Kosminski, if these are using what Len has recently published about preservation of spectral knowledge, and what this would mean for the artifacts, the sampling artifacts that you mentioned can be an issue.
Oh, it's a little bit embarrassing. I'm not exactly sure what Len published about the preservation of spectral knowledge. It's not the poster that you had in the ENC, I guess. There's
so maybe it's a question for Len then, or in combination. You're working together, right? So I was curious if these have made it into 5D processing.
So maybe the part that I can answer definitely, and then Len can maybe say something about this. We used SSA because really this SMFT approach is only working with SSA, and so far NMR pipe is not really using 5Ds as far as I see. I've been also interacting with Sven Huberts from the Wagner lab about it, and maybe add bags and the SMILE framework could also expand what they can do right now. But so far we really basically stuck to the SSA, which works well in our hands. Yeah, and sampling artifacts, that's something, it works pretty reliably, and we really can get away with a very sparse sampling. So that's on the order of below 0.1% of the data points. So I think it boils down to having enough points, and that depends on how many data points you expect. So how many amides, for example, you have, rather than the sparsity as a percentage.
Then do you want to add anything to that, or?
Yeah, the question's a really good question. The preservation of spectral knowledge depends a lot on the details of the reconstruction and whether it preserves all of the information that is there in principle in the time domain. The only thing you can do to that is make it worse when you reconstruct the data, but many of the protocols that have been established turn out to be extremely robust in that reconstruction. So some of them are better than others. We haven't done the Monte Carlo to dig into how well the reconstruction works in the 5D methods. But if you compare things that are just sort of generally available in NMR pipe, they tend to be really robust, actually. So I don't know if that actually answers your question.
Yeah, it does. Thanks.
Yep.
Good. So I think we're half an hour past 12, and do we usually have any informal session afterwards, or?
Oh, it's up to you. I mean, if you want to stay, I mean, I'm happy to do so. But anyway, I would like to thank Rasmus and also Paul for giving such an excellent talk. Also, thank you to Lauren, Hartmut, and May for being here.
Yeah.
So 2 weeks later, which is 24th of May, we will be hosting Amel Gobert from Tel Aviv University and Enrico Rivera from CERN Florence. So we are looking forward to seeing you again in 2 weeks. So if you feel like staying here and asking more questions, feel free to do so. Yep, otherwise, see you.
Thanks, Con. Could I ask a question for Paul, actually? So the question is motivated by observation of our membrane protein spectra, where we, so far in nitrogen line widths, we haven't seen much dependence in either field or MAS frequency. So if we look at the line width in hertz, it's always about 30 hertz. For some of these samples, we work hard to try to make the samples best we can, and we end up around 30 hertz. And in light of your talk, I also had the impression that basically microsecond motion typically just results in so much broadening you can't detect the resonance at all. So I was curious how we should think about these spectra in your opinion, and maybe the question would be best formulated. So what type of microsecond motion should we be able to detect or expect to detect? Because it seems like in a lot of these samples, it must be faster motions, which are actually contributing to the nitrogen line shape. Of course, it's a little different. We have proton decoupling on rather than just a pi pulse. And it's not R1 row. So it's a little bit different, but still, I guess like most of the motion must be fast, which is contributing. And also curious of your thoughts.
I'm not sure you can actually learn that much from the line widths per se about dynamics, because like R2 is always, or the apparent R2 prime or whatever is always much larger than R1 rows. So even in deuterated ubiquitin crystalline spinning 55 or so, if you measure R2s,